Hi students. So in the last class we discussed about the capacitance of the parallel plate capacitor when there is an air between the plates, right? So I'll just give you a quick recap. So when there is an air between the plates, the electric field only between the plates it survived E naught. So I'm going to split here. This is for air and then one for medium. Okay, so when there's an air between the plates, so electric field between the plates, I can simply write my E naught equals to sigma by epsilon naught. This is going to be Q by A epsilon naught, right? So Q is the total charge, A is the area of cross section of the plate, epsilon naught is the permeability of the air when there's an air between the plates. So next the potential, I can simply write this by equation 1. The potential we may write is equal to E naught into D. So if I substitute my E naught value here, I can simply write my Q into D A epsilon naught. This is for equation 2. Next the capacitance, the presence of air, I can simply write Q by V naught equals to, it's going to be epsilon naught A by D. So this is the electric field between the plates when there is air between the plates. This is the potential between the plates, and this is my capacitance of the parallel plate capacitor when there is air between the plates. So epsilon naught is called the electric permittivity or permittivity of the air or vacuum. Okay, so it's a constant. So next when I insert the dielectric material of dielectric constant between the plates. So this is the space is filled with the dielectric material of dielectric constant K. So I can simply write my K. Okay, what is my dielectric constant? So epsilon by epsilon naught equals to epsilon R. So this is the permittivity of the medium, this is the permittivity of the air. So this is called relative permittivity. So permittivity is nothing but the ability of the medium to permit the electric field lines. So this is my relative permittivity. So this is nothing but the dielectric constant. This K is called dielectric constant. Okay, so if the parallel plate capacitor is completely filled by the dielectric material of dielectric constant K, what's happening to my electric field? So if I insert this dielectric material of dielectric constant K, my electric field will become the presence of medium. So my electric field between the plates, I can simply write E equals to sigma by epsilon. Because of the presence of air, I use the notation is called epsilon naught. So epsilon is nothing but the permittivity of the medium. This is equals to Q by A epsilon. This is my equation 4. Right? So next I just want to write my potential between the plates. So V equals to E into D. So if I substitute this here, I am doing Q into D by A epsilon. This is my equation 5. Right? So next I am going to simply write my capacitance in the presence of medium. So Q by V. If I substitute this V value here, I can simply write my Q is equal to epsilon A by T. So this is my equation 6. So my capacitance of the parallel plate capacitor, the presence of the material of permittivity epsilon or the dielectric material of dielectric constant capital K is C equals to epsilon A by D. So these three equations when there is air between the plates, these three equations when there is a medium between the plates. So listen carefully, for the same dimension A, D, D, I can increase the capacitance of the capacitor by changing the value of the epsilon value, the permittivity of the medium. So if I increase the nature of the material, if I increase the nature of the material inserted between the plates, I can increase the capacitance of the parallel plate capacitor. So what I am going to do here, I am going to equation 6 divided by 5. So I can simply write C by C naught equals to epsilon by epsilon naught equals to K. So this is my equation 6 divided by 3, right? C by C naught equal to K. So my C equals to K times C naught, which means if you are increasing my dielectric constant by some factor, your total capacitance also increases. So by inserting a high dielectric material, we can increase the capacitance of the parallel plate capacitor. So what's happening if I divide these equations, electric field, if I divide my equation 4 by 1, because I am going to compare this electric field between this E and E naught. 4 by 1 is going to be, because this Q and this Q gets cancelled, A gets cancelled, is going to be E by E naught equals to epsilon naught by epsilon. I think I am correct. So this is going to be 1 over K, or I can simply write, I think I am correct. So E, it's inversely proportional, right? It's going to be 1 by K. So I can simply write this equation as E naught by E equals to K. So according to this equation, when your dielectric material of dielectric constant K increases, your capacitance gets increases. But according to this equation, if the dielectric constant increases, my electric field between the plates it decreases, right? So according to this equation, so C by C naught equal to K here, this is E naught by E equal to K. So next, what happened to my potential? So I am going to divide my equation 5 and 2. Equation 5 divided by 2. If I divide these two, I am getting my value of same. V by V naught equals to epsilon naught by epsilon equals to 1 by K, or I can simply write V naught by V equal to K. So in this case also, if I increase the nature of the material, which means the dielectric constant, my potential also decreases, right? So only the capacitance will get increases when increasing your capacitor of capacitance, the dielectric material. So these three relations are very, very important for your exams. Okay, so next I will teach you quickly the capacitors and series and parallel combination. So first I start with capacitors in series. So we have a capacitor C1 and C2 connected the potential here, right? So capacitor C1, C2, the charge is Q1 and Q2, right? So for example, in this case, I am going to apply my potential V here. So my potential drop across this, see, listen carefully, since the series combination, the charge entering here Q is same for this capacitor also. In series combination, charge will be the same, but the potential will be the different, because the amount of potential drop across this will be V1, the amount of potential drop across this will be V2, because in the series combination potential will be variable. So I can simply write my net potential according to your Kirchhoff loop rule. Whatever the potential you applied here, the same potential will drop across these two capacitors. So I can simply write my V is equal to V1 plus V2. We already know Q is equal to C into V, for V is equal to Q by C. So for I can simply write Q by C equals to Q1 by C1, sorry, Q by C1 plus Q by C2. So I can simply write my 1 by C equals to 1 by C1 plus 1 by C2. Therefore, C equals to C1 C2 by C1 plus C2. So this is the equivalent capacitance of this series. I can simply write CS. So this S stands for series. So this is the equivalent capacitance of this series combination. So this is how it change. So this is exactly opposite of your resistors. So next I'm going to start parallel combination. Parallel combination. So we have a capacitor of capacitance C1 here. We have another capacitor C2 here. C1, C2 connected with a cell of potential V. Listen carefully, in the parallel combination my potential won't change because whatever the potential is applied here, the same potential drop across this, the same potential drop across this also. So there is no change in its potential. Okay, if there is no change in its potential, what's happening? My charges flow from here to here is going to be Q. Up to this point is just a total charge. So here my charge is splits. Here the charge entering is going to be Q1. Here the charge entering is going to be Q2. This is very, very important, right? So in the series combination, potential varies. In the parallel combination, charge will varies. So I can simply write the total charge Q equals to Q1 plus Q2. We already know Q is equal to C into V. I can simply write C into V equals to this is my for parallel combination. I can simply write C1 V plus C2 V. So V gets cancelled. Cp equals to C1 plus C2. So this is the equivalent capacitance for this combination. If you have n number of capacitors, you have to add till n. So if you have n number of capacitors here, you have to add 1 by C1 plus 1 by C2 plus 1 by C3 till n. So be careful. So without this, you cannot solve problems, right? So in the series combination, potential splits, potential varies. In the parallel combination, your charge will be various. So this is very, very important for your problems, not only for CBSE exams as well as JEE or NEET. So this is very, very important. So based on this series and parallel combination, I will do the problems in the next class. So I just stop at this point. So if you like this video, share with your friends and subscribe our channel for the more content. We'll meet the next video. Thank you.